My name is Borjan Gagoski, and I will be presenting our work on automatic detection and reacquisition of motion-degraded images in fetal HASTE imaging at 3 Tesla. I have nothing to disclose. Fetal brain MRI is hindered by unpredictable and random fetal motion even when using single-shot FSC acquisitions like HASTE. What usually happens in clinical settings is that the MRI technologist inspects the images in real time, and if some are motion degraded, the entire stack usually needs to be repeated. We can see that in the video on the right. This results in long acquisition times, during which the pregnant mother needs to lie still in the confined space of the scanner. To that end, the goal of this work was to develop an acquisition pipeline that automatically, with no human interaction, detects and reacquires only motion-degraded slices and not the whole stack. To achieve this goal, we first developed a convolutional neural network that performs an automatic image quality assessment of fetal brain HASTE images. We formulate the MRI quality assessment as an image classification problem. HASTE images are classified as good or diagnostic, bad or non-diagnostic, and those who contain no brain within the field of view. The pie chart here shows the distribution of our labeled dataset, which included about 10,000 manually labeled fetal HASTE images obtained from the clinical archives at VCH. Here we show representative images from each of the three categories. We first trained our CNN using supervised learning by minimizing the loss between the network prediction and the ground truth label. One limitation of supervised learning is that it requires large labeled datasets for improving the accuracy. Labeling this dataset is a difficult and time-consuming task. On the other hand, we currently have access to more than 200,000 unlabeled fetal HASTE images from the clinical fetal archives at VCH. To utilize this unlabeled data, we propose a semi-supervised learning methods which impose regularization on the network by learning feature from the unlabeled data. When evaluated on a test dataset, our CNN achieved around 85% accuracy and area under the receiver operating characteristic of about 0.9. More details about the CNN can be found in our recently published Mukai paper, cited here. Next, we modified the HASTE sequence in order to perform real-time quality assessment of the HASTE images. To achieve this, the IQA CNN was run on an external GPU-equipped computer and hooked to the internal network of the MRI scanner via 1 GB Ethernet hub for efficient communication. At the beginning of the TR, the HASTE readout is played, and immediately after that, the reconstructed image is sent to the external computer. Python scripts receive this image, run the CNN, and an IQA score is computed in about 30 milliseconds and sent to a buffer. At the scanner, a DICOM image is created and displayed, just like when running a standard HASTE scan. After some idle time due to SAR constraints, the sequence requests the IQA score, and Python scripts on the external computer send the score back to the sequence. This score, along with the slice index, is saved by the sequence for later use. At this point, one TR is completed. If there are more slices to acquire, the whole workflow is repeated for each slice. When the prescribed stack is completed, the sequence sorts all the IQA scores from all the slices and reacquires only the slices with the NREAC worst IQA scores. NREAC is a number defined by the user before the scan starts. This concludes the closed-loop system. Now let's move on showing some of the results. All MRI experiments were done on a 3 Tesla Siemens Skyra system and VCH. Phantom experiments were performed to ensure that the real-time communication between the external computer and the sequence works properly. The closed-loop system was then tested on 3 pregnant moms who signed informed consent forms, which are approved by the IRB at BCH. More experiments were scheduled to take place, but unfortunately we could not do them because of the COVID-19 pandemic. And finally, I show here some details of the image of the HASTE imaging parameters. Here I will show results that show the feasibility of our methods in utero on a fetus with gestational age of almost 39 weeks, where the number of prescribed slices was 10 and 6 slices were to be reacquired. Here I show the 10 prescribed slices along with their corresponding IQA scores. Scores in red represent the 6 lowest scores, and we can see how the sequence correctly reacquired only those 6 slices. Here we show more examples, this time from a 29-week-old fetus where the HASTE stacks were prescribed with 20 slices and set to reacquire the 10 worst slices. Here I show a representative image from an axially prescribed HASTE stack where slice number 14 was motion degraded and hence received a low IQA score. The reacquired slice was not motion degraded and of great quality as reflected by the IQA score. Here is another example from a different HASTE scan prescribed sagittally to the fetal brain. Here slice number 6 was motion degraded and received an IQA score of 0.134. When the same slice was reacquired, the fetus did not move and the IQA score was almost 1. In conclusion, we have demonstrated a closed-loop system that automatically detects and reacquires motion-degraded fetal HASTE images of the brain. This improves the current clinical fetal MRI workflow by providing savings in the overall scan times, as only bad slices are reacquired and not the entire stack, and also by providing objective means of determining which slices are bad so that the MRI technologist doesn't need to do this decision in real time. The current methods don't provide the means to tackle the biggest problem in fetal MRI, which is mitigating fetal motion. However, the proposed infrastructure can be expanded to tackle this problem. So this is exactly what we're attempting to do next. Specifically, we already have implemented a version of the HASTE acquisition that embeds low-resolution 3D EPI readouts within the idle time of the HASTE sequence, as it can be seen in the simulated pulse sequence diagram shown here. The imaging parameters of the EPI VNAVs are shown here, enabling whole fetal brain coverage at 5 mm isotropic resolution in about 0.7 seconds. We're currently developing a CNN that uses the EPI VNAV volumes and provides accurate estimates of the fetal head post HTR. This CNN would also run on the external computer shown earlier, and the infrastructure described earlier can be easily expanded to readjust the field of view coordinates and track the fetal head in real time. With that, I would like to thank you for your attention, and I would take any comments or questions.